All right, it's 12 o'clock and it's Wednesday, so it's time for the Iowa Learning Farms Conservation Webinar. I'm Matt Helmers with Iowa State University. Uh, Happy to be here to help facilitate the webinar today. And we have a really great topic, important topic. We have Dr. Merrin Macrae, that's with the professor in the Department of Geography and Environmental Management at the University of Waterloo. So she's coming to us from the country up north, and she's been really doing some great work on looking at phosphorus loss into the Lake Erie watershed. So her talk today is on One Size Does Not Fit All, targeting conservation practices to reduce phosphorus loss risk in the Lake Erie watershed. As always, if you have questions or comments, please type those in the chat box and we'll get those to Dr. Macrae at the end of her talk. So with that, Merrin, the virtual floor is all yours.
Great, thanks. Such a pleasure to be here. Okay, so I'm going to just jump right in. So, okay, so we've all seen slides like this before, the gratuitous green slide. Lake Erie, we know, has a very long history of water quality impairment. And we know that we saw a lot of improvements in water quality in the 80s and the 90s that were really driven by improvements in wastewater treatment and other industrial sources. But since that time, we know that Lake Erie has also undergone a period of reeutrophication over the last 20 years. And today, we also know that non-point sources are the dominant source of phosphorus to the lake. Now, we've been applying, in light of this, we've been applying BMPs throughout the watershed, but we're still not reaching our objective. When we look at the bloom severity over time, we see that we're not getting where we want to get. So why is this? Now, some of it could be climate, some of it could be legacy, but some of it may be that we're not doing enough in terms of conservation practices or BMPs, but it may also be that we're not using the right BMPs in the right places. And I want to talk about that today. So we know, we've probably also heard this. We've been told that there is no one silver bullet. We often get asked, what's the one thing that we could do? There is no one silver bullet. And we also know that stacking has been shown to work. So stacking, where you apply multiple conservation practices, and that each one does a little bit, and together they can do a lot. And I agree that this is true. But I also think that, oftentimes people aren't necessarily sure within these which one might be optimal or which grouping might be optimal. And I think that we can be more strategic. We have to realize that there is a cost to BMP implementation and application, and simply stacking things on, some of which might not work or might cancel out the benefits of others, isn't fair. And so we really want to do better than this. So we've taken a look at trying to strategically optimize BMPs within the Lake Erie watershed. And so how we did this is this really started out with a geographic analysis of zones, or sort of ecoregions within the watershed. So it started with microclimates. So when we think about climate variability, we kind of think about the Great Lakes region as one particular region, and then we might think about big differences between here and, say, the northern Great Plains, or if you're thinking about sort of areas more towards the south. But we don't often think about the subtle differences that might exist within our own region that could be really important from a water quality and BMP efficacy perspective. So from a precipitation perspective, we know that there's some wet and some dry areas, but by and large, it's pretty humid in this watershed. In terms of climates, what we're looking at here is mean annual temperatures. And so what we can see is that it's cooler towards the northeast and warmer towards the northwest. And we can see that this is reflected where we've got more growing degree days, so a longer growing season towards the southwest, and it's a little bit shorter in some of these other higher elevation and in this case, a more northern landscape. We also can see what's interesting, though, is that what we also see is a longer period of snow cover duration. So these guys get more of a true winter. Whereas when we get down towards these warmer areas, we start to see where we get some snow, then we might lose the snow. Then we might get the snow, then we might lose the snow. What are the implications for how and when and where water moves? And I'm going to come back to that. So it's not just about climate. What about landscape? So we also see really some differences across the landscape. Notice that when we look at our elevation and slope, we have these really low-lying flat areas towards the, really surrounding the lake. And then you start to get into higher elevations. And we also see coarser textured soils in these landscapes, whereas the stuff that's flat and around the lake tends to be more of those heavy lacustrine clays. And so we can see that there are some landscape differences that might also be present that, again, would impact how, when, and where water might move and nutrients. When we looked at land management practices, so that we looked at different production systems throughout the watershed, and the presence of corn soy, so that yellow really pops out at the screen at you. But we can see that certainly that dominates. As we start to get into our cooler areas and our more sloping ground, we definitely start to see more winter wheat and greens getting into the rotation. Another feature that we see is differences in drainage. And as we really get towards that southwestern end of the lake, we see a significant amount of the land has assisted tile drainage. And as you move away into those sloping grounds, you see it, but you don't see it as readily. So what we did is we put all of this together to say, okay, so we have climate differences, we have some drainage differences, we have some landscape differences, put it all together, and we used a clustering analysis. We used a k-means approach, basically, to delineate some management zones. And so what we found is we came up with 4 zones, and we tried this, could we break it into 2, 3, 4, 5 zones? And we kind of settled on 4. And what we found is we didn't find clear zones, but we found some end members. So we found a clear difference between the northeast and the southwest. And then we sort of had these transitional areas in between. And so what we found is these clearly differed in their topography and soil textures, but also their climate. So this is some examples of what it might look like in the the upper Thames or the central and upper Grand River watersheds. Whereas this is maybe something that you might actually, sorry, my screen went, you might actually see towards the southwestern end and that southwestern Ontario and northwestern Ohio. So you can really see a difference in that landscape and also those climate characteristics. So what we started to do was compare how is water actually leaving the fields and why might this matter for phosphorus transport? And so we know that water can leave the edge of fields either on the surface or in the subsurface. And we always concerned ourselves with surface erosion because this was understood to be the primary phosphorus loss pathway. It was about erosion, particulate losses, keep that phosphorus on the fields, get it underground, and let the soil do its job. But we now know that that tile drains can actually become an important pathway for that phosphorus to leave at the edge of the field. And that phosphorus can bypass the natural filtering ability of the soil. And that can be problematic. So we wanted to know, well, how much of that water is actually leaving in the surface and how much is leaving in the tile? And so we did this over about a 4 or 5-year period. And what we found is that from a water perspective, probably 80% of our water across our fields, and although there might be subtle differences in years, for the most part, it was pretty stable, that about 80% of the water, which is shown in blue, left underground in tile drainage and maybe 20% left in surface runoff. And we also know that a lot of that surface runoff was concentrated to really wet periods, peak flow conditions, and in the northeast, that's really around that snowmelt piece. Whereas the southwestern end, again, peak flow, but a little more evenly distributed throughout the year. when we actually looked at our nutrients, we found something different in terms of flow paths. In the north, so first of all, in both of these landscapes, our particulate phosphorus dominates, but it's more significant in the northeast than in the southwest. So a higher proportion of the total phosphorus in the southwest is dissolved compared to the northeast, but particulate is still the dominant form. Okay, so when we looked at our dissolved P, that little bit of the runoff actually accounted for most of the dissolved phosphorus losses. So although the tiles accounted for a significant pathway, like not quite half, it was because so much water was moving through the tile, and the surface runoff was really the predominant pathway. Whereas when we went down into those southwestern clays, they were kind of the proportion of dissolved reactive phosphorus losses that left the field was really proportionate to how much the hydrological losses were. So it was like 80-20, sort of like the hydrology was. Now, for total phosphorus, it tended to be more evenly distributed between pathways. So we definitely know that tiles and surface are important pathways across the watershed, but they're a more important pathway in the southwestern end. Now, ultimately, we need to manage in both of these pathways, but your priorities and your selection of management practices might have to differ depending on where we live. So when we started to think about what BMPs or conservation practices might be suitable, we know that there are a lot of different things that farmers can do to reduce phosphorus losses on their farms. But some of these, like I said, might be more effective, and they might improve things under one condition or landscape, but make things more problematic or not do much or have unintended consequences in another. And winter conditions in particular are something that are really poorly understood. We don't really understand what's happening in winter as well as we do at other times of year. And a lot of the winter research that we've typically drawn on has come from areas that have really more severe winters, like the Nordic countries or the northern Great Plains, and not necessarily areas that we have a winter, but it's a very different winter than those other places. So we took a look at some examples looking of conservation practices, and we looked at where things maybe were similar or different across landscapes. So we've all heard of the 4 R's. So that's where we're looking at the right type, time, place, and rate. So when we start to think about the right rate, so one thing that we found consistently across our sites was that there was higher runoff phosphorus losses when you had higher soil test P. And so we also know that if you can draw down that phosphorus, it is going to lessen what we lose in runoff. And that seems to be, that concept is consistent everywhere. But the degree to which that alone makes a difference could differ across landscapes. And we're sort of looking into some of these things. And so we also know that not everybody has as much room to move. So at the really elevated sites, it's a no-brainer. We've got to get those down. But at areas that are more at agronomic thresholds, we don't have as much wiggle room. And so we really have to look at this in combination with other things. So another thing that we looked at was actually where the phosphorus was placed, so the right place. And so we did some experimental work both in the lab and in the field where we've looked at phosphorus that is broadcast on the surface, and we've looked at environments where it's placed in bands in the subsurface. And what we actually found, both for phosphorus and nitrogen, that applying it in a band considerably reduced phosphorus and nitrogen losses in tile drainage. And the reason for this is that by localizing it and placing it where the plant needs it, basically you're disconnecting that hot phosphorus source from the preferential paths that will route that into tile drains. So you're kind of disconnecting the source from those really effective pathways. So now, in terms of things like that, whether or not you should incorporate fertilizers as opposed to, or incorporate fertilizers or manure as opposed to placing them or injecting them under the ground. So, you know, when we start to think about the incorporation of materials, the trade-off with incorporation is it comes with, there's the tillage aspect, and then there may be trade-offs associated with that tillage. So I'm going to come back to that in my next slide. In terms of timing, we know that at the time of seeding is best, and we know you should never apply on frozen ground, but this becomes most important in these areas where you tend to see that really significant snowmelt period and those snowmelt peaks when this stuff can just sit on there, and then the next time the runoff event that happens, off it goes in surface runoff. So that's definitely something that should be avoided. And we know that in the Northeast, because of that shortened growing season, the later in the fall you push things, the more problematic it gets that you're going to lose that fall application with your winter-related losses. And so it sounds like we have a little more flexibility in the Southwest, and we can go a little bit later, but ultimately putting it with the seed at the time of planting is optimal across the landscapes. So I talked about no-till a moment ago. And so we've done a few studies in Ontario where we've looked at no-till and till sites on tile drain phosphorus losses. And on the study on the left was in a sandy loam, and the study on the right was in a clay. So this was in the southwestern, or this was in the southwestern end, and this was in the northeast. So this was a sandy loam, and this is in a heavy clay. And what we found is that our no-till increased dissolved reactive phosphoruses, so our no-till with a cover crop increased dissolved reactive phosphorus losses, especially when he surface broadcast as fertilizers. But we didn't see that same effect in our sandy loam sites. What we found is it had no effect on dissolved losses. But what we did see is that particulate losses at our tilled sites tended to be higher when at both sites. So the effects of till and no-till on dissolved reactive phosphorus losses through tile drainage seems to differ, but what we also find is that in both cases, you can increase particulate or erosion into tile drains, and this is problematic. So we also want to think about trade-offs between dissolved and particulate forms of phosphorus. We're really concerned about dissolved reactive phosphorus because it's bioavailable, but we have to remember that total phosphorus can also be bioavailable, some of that. So we want to be wary of trade-offs. The optimal situation is to stay or to get as close to no-till and conservation till to avoid those particulate trade-offs. But if you can inject that phosphorus underground or place it in the subsurface, you avoid situations like what we're seeing here, where we're really seeing a lot of those incidental losses where the farmer applied phosphorus on a surface broadcast in the fall, and it was all lost throughout the non-growing season. Cover crops are another thing that's been talked about widely. So we know that cover crops offer a lot of benefits. We know that they build soil health. They can reduce phosphorus losses and trade-off. I think these photographs really show a lot, looking at the field without cover crops and the field with. The problem is that in a winter climate, they can freeze. And when they freeze, they can release a lot of dissolved reactive phosphorus in runoff waters. And so this is something that they've seen in the Nordic countries and also in the northern Great Plains. So then people have questioned, well, should we put cover crops on our fields in light of this challenge? And the thing to think about is, this is where I brought up earlier that our winters are not the same as some of these other winters. We get moderate temperatures. We definitely get cool temperatures, but we get considerable snow cover in some areas. And that snow cover can actually insulate the ground and the plants. And so this can moderate the freeze-thaw cycles that these things are exposed to. So we did an experiment. And so what we looked at is we found that really observational data showed us that underneath the snowpack, you might see maybe -4 that the plants might be exposed to. Whereas when you're in a snow-free environment, you might see those much more plunging temperatures. So sorry, I'm in Celsius here, but -18 Celsius. So what we did is we did some experimental work where we froze froze and thawed different types of cover crops, different species that are prominent around here. And we looked at a moderate freeze thaw and a more severe one. And we found that the more severe frosts absolutely led to a bigger release of dissolved phosphorus from the species, but that it varied with species, and that your tender species that we know winter kill were more vulnerable to that loss, whereas our hardier species were not. We also found that in areas where you were prone to ponding and you had a lot of standing water, that made the crops more vulnerable to leaching of phosphorus into runoff waters, whereas if you were not necessarily exposed to a lot of flooding, they didn't lose as much. So this told us that the vulnerability of cover crops to winter loss really depend on the cover crop type, the extent of that frost, and the degree of moisture content. So how can we optimize this across regions or even just within different fields in a region? So what we see is, remember, let's go back to this. So we have really, we can lose our snow up in here, but we often have a pretty good period of snow cover when our temperatures are really, really low. Whereas these sites can be more prone to those freeze thaw cycles, and they may or may not have snow cover. So when we look at them, this is taken in the blue northeastern area, and this is taken in the southwest. These are taken in the southwestern area. The Northeast is more likely to look like this for longer and this for shorter periods of time, whereas this is what you're more likely to see in the Southwest, and you might not see this for as long. So really, although these Southwestern areas are warmer, they actually might see more frost on their cover crops than up in the Northeast, where we have this blanket for a bigger period of the time. So what does this mean? Well, when we think about these areas towards the northeastern area, we're sloping ground, lots more phosphorus being lost in surface runoff. Those erosional processes are at work. It's a lot of that particulate phosphorus. So the fact is, it's a bit of a gamble, but you have the snow cover to insulate. We know that particulate losses are the biggest challenge. Cover crops are a really good idea here. I think also cover crops are a good idea in the southwestern end, but you want to be careful with what crops you use, and maybe and in both landscapes, maybe thinking about fields that are really prone to extended periods of flooding, where the crops may be vulnerable, they're steeping like tea and they may lose a lot. You want to be a little cautious with those. So I think if we use them carefully, I think at the end of the day, cover crops are a great option, but we just have to use them carefully so that we don't have some of those trade-offs. So what we did is, this is actually a really cool summary diagram that the CSA News did based on our paper that was published to show our findings in an infographic. And so what we talked about in this paper is a 5-step process to really optimizing and targeting phosphorus management regions for conservation practices in the Lake Erie watershed. And this is something that we used in the Lake Erie watershed, but is adaptable to other watersheds. So the idea was to refine phosphorus management regions, which we've been working on here. We've definitely got endpoints, but we need to do a better job with those transitional areas. And then we're developing region-specific guidance through improved practice catalogs or fertilizer recommendations. Okay, so we're saying this works a little better here and this works a little better there. The idea is to next refine that region-specific guidance, because we also need to have trials. We were looking at, some of our guidance was based on our own field sites, but some of it was also based on what we pulled from the scientific literature and other studies. We need to actually target these questions and optimize with some studies to validate what we're seeing. And we need to communicate these results to producers, and we want to adapt. We want to really implement an adaptive management framework as we do this. And again, this is just for the Lake Erie watershed, but it's absolutely something that can be applied elsewhere. So the key messages really are that different regions have different climates and landscapes, and this affects phosphorus loss through the environment. And we know that the efficacy of conservation practices can differ regionally, and that we've put together different phosphorus management practices, management zones that are based on climate and landscape, so that we can't necessarily say what exactly is the perfect thing to do on a given field. That really is becomes something to talk about, but we can definitely come up with some general principles where of conditions or places where conservation practices or bundles work more effectively and less effectively. And I think, again, we want to start to do this across different watersheds and really keep moving towards this 5-step adaptive management framework. And with that, I'd like to thank you for your attention today. And I'm going to pass over to Matt for the next few slides.
All right. Thanks, Merrin. All right. So if you are on and need a CCA CEU, please email Elena Whitaker, ALENAW at iastate.edu by 5 o'clock today. Please include your name, the name you entered to watch the webinar, and your CCA number. Again, ALENAW at iastate.edu. I'd also feel free to get any questions that you have in for Dr. Macrae into the chat box, and we will get those to her when we finish up the next couple slides. Let's go to the next one, which is the voluntary demographic survey. If you watch this webinar live and are willing to fill out the voluntary demographic survey, we would greatly appreciate it. Only one survey response is needed for all 2024 webinars. You can go to iowalearningfarms.org/survey or scan the QR code. So iowalearningfarms.org/survey or scan the QR code and put a plug in for next week's webinar. And we have Tim Rosen, that's the Director of Agriculture and Restoration in Shore Rivers out in Maryland. He's going to talk about some work they've done on pay for performance, cost share alternative to increase non-point source pollution reduction. Encourage you all to attend that. About a year ago right now, those of us in the Conservation Drainage Network visited Eastern Shore of Maryland and got to see some of the work Shore Rivers does. And so it's really great information. Again, if you have questions, feel free to type those in the chat box. I'm going to take my prerogative as a moderator to ask the first question. Merrin, you've done a lot of work on tile drainage and phosphorus. And I think we've done less of that here in Iowa. But I mean, as you've looked at the literature, I guess how similar or different do you think some of these results might be across the kind of the tile drain corn belt of the U.S.?
Sorry, I'm not
Yeah.
like how applicable are some
Yeah,
of these
yeah,
things to
yeah,
those?
applicable to that. Yeah.
I think it is more broadly applicable. Like we're playing it safe to say in the Lake Erie watershed because that's where most of our work is. But I think if you can think about landscapes that would be flat clays, you know, you might see like the way our tile drains are behaving in a sloping loamy system as opposed to a flat heavy clay. I really do think that some of what we're seeing is it can easily be extended to those areas. Now, you have to couple or layer onto that the idea of the winter. And so you really do have that north-south gradient. And so the farther north you go, the more those winter processes are going to come into play. And the farther south you go, maybe not so much, right?
Yeah. Next one, can you go to the slide that kind of illustrates kind of the particulate P with the tile drainage? And I'm assuming on the
this one? No. Which one?
No, it was that one with the graph that
Oh yeah. Yeah. I know I kind of had to go through that fast. I'm really sorry.
That's okay. Yeah, that one.
Yeah.
Okay. And this is that total P is in that's just in the tile drainage, correct?
Correct.
Yeah. And is do these have intakes on them, or are they just pure kind of what we call subsurface drainage systems?
Pure, there's no
Yeah.
surface inlets into them.
Yeah. So what is that from kind of the macropore flow, you think that we're getting some sediment movement through those macropores? I'm
That
just
I
somewhat
don't
curious.
know. I mean,
Okay.
I think it could be. Like, I
Yeah.
guess that's a good question, and that's something that we're working towards now.
Okay.
Because I think for, people a lot. I mean, part of it is that the conversation comes up, like we worry about dissolved reactive phosphorus and tile drainage, we worry about the bioavailable, and we think, oh yeah, it's all, like when we think about sort of the processes that are governing this, you'd think that there wouldn't be any total you would think that your dissolved would equal your total or be
Yeah.
closer to it, and that there wouldn't be much particulate in tile drainage. And we also looked at the different forms of phosphorus. So you can look at the total, like, because remember that total phosphorus is made up of the particulate phosphorus, but there's the dissolved reactive phosphorus, but also the dissolved unreactive phosphorus.
Hmm.
So that we've also looked at whether or not of the total phosphorus, you could make the argument that it's still dissolved and it's just the unreactive, but it's not. It's really
Yeah.
particulate. And you can see that if you actually look here, the TSS, which that's total suspended solids or total suspended sediments, they're absolutely higher. So the fact is particulate is absolutely moving into the tiles. And yeah, I think some of it really is moving through those pathways. So
Okay.
understanding sort of where it's coming from and how it's moving is somewhere where I think some additional work is needed.
Okay. Yeah, it's fascinating. And even looking at that, like the fraction of uh, DRP to total P, um, I guess that ratio is maybe less than what we see in some of our drains, I think in Iowa, that a larger fraction of that total P is reactive P, if that makes sense.
Right. Okay.
Yeah.
Yeah.
Yeah. That's
Yeah. Yeah. And that's what we've seen. But I'm just
okay.
finding where we are,
Yeah.
it's not because we went into this assuming that was the case. And
Yeah.
then we were really kind of surprised to see, well, actually, the particulate is pretty important.
Yeah. Yeah. Very fascinating.
Yeah.
Okay. One said, well, there was a question. I guess kind of maybe clarifying a little bit how you be careful with cover crop use. Once somebody picks a cover crop type, it will go on an entire field.
Yeah. Okay. Great question. So I think what I'm thinking about is I think there's a couple of things, and there's you only have so much time to get into
Yeah.
things during these webinars, and this is a culmination of
Yeah.
I don't know, more than 10 years worth of studies. So I think first of all, it has to do with selection of cover crop. Number one, just selecting the species at all. Like, what are you going to use? And I understand that phosphorus is not the only reason why somebody may choose a cover crop. They may have other reasons in addition to phosphorus management why they might like to use a particular cover crop. And I get that. But I think if you're just looking at phosphorus management alone, the first thing is to look at species. And so be aware of the fact that tender species are more vulnerable to phosphorus losses. So if you start to think about the why might this cause problems versus not? So if I'm in a situation where I see freeze thaw, and really plunging temperatures with no snow cover, the fact is those things are going to freeze and they're going to die, and they're going to release a lot of that phosphorus to runoff water that comes into contact. Well, one thing that we found is that even around here, oftentimes, okay, so I didn't talk about this one study, but Tatiana Lozier was one of my former students, and she did a study where she looked at the timing of when these things were being lost. And what we often found is that what the plants released didn't translate to edge of field losses, because as soon as that came into contact with the soil just took it up. And so the areas like in the Canadian prairies or some of the northern Great Plains where we've seen a lot of the issues with cover crops, it's first of all, those sites have 4 feet of frozen ground. And I don't know if you can hear my St. Bernard snoring,
No.
but I'm so sorry.
No. No. I don't.
All I can
I
hear
don't.
is a
I
very
don't hear it.
scary
No.
loud dog.
I don't.
Okay, so I lost my train of thought. Yeah, so a lot of it is they have these severe frosts, and then you have water that's sitting on the surface as it waits to run off. It's sitting on that frozen ground. So it's kind of the perfect storm. Whereas where we are, you're getting freeze thaw, and a lot of it is going into the soil. But if you have a situation where really there is a lot of ground frost and water, crops freeze up green, they get plunging temperatures, and then the next time they see any activity, it's standing water on the fields. That is a recipe where you could lose a lot. And so the thing is to think, okay, so maybe tender species, even though they're convenient because they're frost killed, they might cause issues for phosphorus losses. So maybe thinking about hardier crops might be optimal. The other thing that I didn't talk about was termination. So a lot of people either frost, they'll allow frost to kill it, or they'll use an herbicide, like give it a chemically terminate crops in the fall, so that they're not such a nuisance to deal with in the springtime. What we actually found, and this is James Kober, who is a former student of mine, and what James found is if you terminate, you will absolutely lose it. So terminate. So that's where you can say, okay, well, so what do? Do I terminate or do I leave it green? Well, if you're in an area where you know that you're going to lose it and it is vulnerable to runoff water, maybe you think about terminating it so that the rain gets it off of the crops and into the soil before that spring melt comes. Maybe that's a sort of a management option. Whereas if you're in an area where you're in hardier crops, you have lots of snow cover, maybe don't terminate in the fall, because you're probably not going to lose it in the winter. And then if you are going to terminate, maybe do it in the spring.
Okay. All right. Another one. What are the most widely adopted conservation practices you're seeing across the watershed? And maybe if you have any information on how cost share programs look across the multiple, thinking across the two countries between, Canada and then, as we think about Ohio and
Yeah.
Michigan there.
I can't say how they
Okay.
work. I wish somebody was here who could speak to that. I can't tell you. I know certainly some of the things that have been done in Ontario over the last, in Ontario, and there have been lots and lots of cost share practices or cost share programs that have come where farmers can apply for cost share, and there are resources that are allocated to that. And so the cost share might be everything from putting down a cover crop and them paying for seed, or it might be that you may get funds to apply for a new piece of equipment, like maybe you want to get a no-till drill or something like something that you need. So these are some of the things that I've seen, but in terms of the various programs, I can't speak to that. But in terms of the things that that we're seeing a lot of, I mean, certainly there's always going to be the erosion control. So people are obviously using erosion control, whether or not it's WASCOBs, so water and sediment control basins, are something that's pretty common around here. And certainly riparian zones and buffer strips are certainly things that are widely used. In terms of on field, certainly cover crops are something that's really taking off. Nutrient management, certainly something that's widely being promoted is the province of Ontario. They've developed something called Plato, which is the phosphorus loss assessment tool for Ontario. So that's where they took the P index and they tried to optimize some of these the risk of phosphorus loss based on some of the things that I've talked about today, and expert knowledge. So a big team of them put that together. So that's pretty cool. Certainly trying to get people towards nutrient management, thinking about applying what you need for that crop or crop rotation based on what you have in terms of soil fertility and other things is sort of where we're trying to get people. I mean, obviously, I know subsurface placement is something that I think is really great, but I understand there are logistical challenges associated with that, where it can be a lot slower, and it's not necessarily something that as many people can do. So the question is, what do we need to do to get there? And that I can't answer, and that I turn over to people who can figure that out. So
All right, great. There was another one here: with the increasing tendency toward frequent and heavy winter rains and subsequent runoff, it seemed likely that soluble P release from tender cover crops could indeed leave the field via surface runoff and a preferential flow through tile.
Sorry, are you asking me, is it likely or
Yeah,
unlikely?
I guess, is it likely? Yeah. Yep. I
I
guess,
don't,
yeah.
well, see, I think if we're starting to get, so that's the trick, right? It is we're going to get warmer winters. We know that we're going to get more rain and heavy rain and on brown fields. So like bare fields. So I think keeping it covered is a really good idea. So I think, and I think cover crops are going to be not only they important now, I think they're going to become more and more and more important in future. But if we do have warmer winters and more freeze-thaw cycles, we might see less snow cover. So the question is whether or not we're going to still get those plunging conditions. So, I mean, it's a bit of a tricky situation. But I think on the whole, as we move into a warmer climate, I think cover crops are going to become more and more effective around here.
Okay, great. That's all right. Those are the questions that we had. Maybe we can put up the slide for if you're on need a CCA CEU, if you can email Elena Whitaker, ALENAW at iastate.edu by 5 o'clock today with your name, the name you entered to watch the webinar, and your CCA number. And I'd encourage folks to tune in next week at noon Wednesday to hear from Tim Rosen from Shore Rivers, talk about some of the work they're doing on implementation of conservation practices in Chesapeake Bay watershed out there in the Delmarva Peninsula, excuse me. With that, Merrin, thank you so much for the excellent presentation. I'd encourage folks, if they have want more specific information, hopefully they can reach out to you. But with that, I can leave you with the last word, whatever your last parting comment is.
Thank you for coming today.
Okay.
It's really been a pleasure to be here.
Okay.